Welcome to EE 380, Fall 2011-2012. I'm Andy Freeman. We're getting closer, for students, we're getting closer to the end of the quarter, so it's a good time to be completely caught up, so you don't have to try to catch up during dead week. We select talks that we think have a very good potential of being extremely interesting and useful to most of you. So, and we think that almost all the talks meet that standard, and today's talk is no exception. So we think this class should be something that. So we think that this class is something you should be looking forward to. So, keeping up shouldn't be a big deal. As you know, a large part of computer science and programming and electronic artifacts is creating languages that make it easier to solve problems. As a result, almost all of us have toyed at one time or another with making a language. But very, very few of us have ever created a language that got one user, let alone 5. That's the way it is. Today's speaker, Gilad Bracha, has been a significant participant in a number of languages that have gotten modestly large numbers of programmers. Today's talk is about Dart, yet another language coming out of Google for some reason. They're doing language design on us, which may prove extremely interesting or teach you how to design your next language a little better.
Thank you. And after that introduction, meet those expectations. But as I said, almost all talks are interesting. So perhaps you need an exception once in a while. So I'm talking about Dart. As you heard, it's a new language that we're working on at Google. And it's really not my work. I joined this team 3 months ago, and this project has been running mainly from the beginning of the year, but probably a couple of people maybe from late November or so. And so I've just started to contribute to this in whatever way I can. So really it's the work of the Dart team overall, which is a fairly significant team. Now, at 50,000 feet, basically the summary is it's a language for programming the web. And what is special about the web? Well, in principle, I believe that there's nothing special about the web, but in practice, there's a lot that's special, and we've actually had arguably a huge regression in terms of the tooling and the overall environment and stuff that we're using to program web applications in the browser. The fact is that making a sophisticated application that runs in the browser that is, competitive with what are considered good applications that are written natively is a very, very challenging thing. This happens once in a while, but it's much harder. People jump through a lot of hoops, and we want to make it easier. There are two really tough constraints on this design. One is that the web programs, there are a lot of people programming out the web. They're not necessarily all Stanford graduates or Google employees. And we want something that's essentially on-site familiar to them. Because we're interested in adoption. And while I have been involved in languages that got broad adoption, I've also been involved in languages that were actually a lot more fun and got no adoption. And so I understand the need. Sorry?
Is that an inverse relationship between the two?
Probably, yeah. So in any case, we want this to be unsurprising to the mainstream programmer. We have another constraint that this thing has to compile efficiently to JavaScript. Which constraint is harder, I'll leave it to you to judge, but they're fairly challenging constraints, really. And so look at everything that comes now in light of those two constraints, please. So the sort of actual technical summary of what Dart is like as a language is it's a purely object-oriented, optionally typed, class-based single inheritance language with actor-based concurrency of some form. So you can yawn now and say, well, what's so special about that? That's been done a lot of times before. Largely that's true, though some of these things really haven't hit the mainstream yet in very wide usages, right? And so we hope to actually do our part in bringing some of these technologies to a wide audience. The one thing that's a little unusual is this business about optionally typed, which has also gotten a lot of people fired up because there's nothing better than a good religious argument about typing to get people interested. The only thing we can do better is argue about syntax, which is even more fun. So optional types, that's probably the main thing I'll be talking about. also talk a little bit about essentially supporting abstract data types without types, or in a dynamically typed language, as it were, which is slightly interesting, and in built-in factory support. All of these things are what's modestly new in Dart that hasn't been perhaps as widely circulated as the rest. By and large, as I said, the language is designed to be familiar and unsurprising. So whoever wants to leave, this is your cue that if you don't think this is one of those interesting talks, I won't be offended. Optional types. So what do we mean? First of all, a bit of terminology. Optional types as opposed to mandatory types. Mandatory types are the types that you know and love or hate, as the case may be, in most statically typed, quote-unquote, programming languages, right? The idea is that the types are required. A legal program has to pass the type checker, otherwise it can't compile and it can't run. And there are many examples of that. I put a couple out here. By no means necessarily intending to disparage them. They have a philosophy about types. But on the other hand, you can read the color scheme as leaving the tyranny of type theory behind and into the sunlit plains of the Wild West of optional typing, depending on your religion again. So, we don't want this, both for our own experience. I've worked with both statically typed and dynamically typed languages, and I have a preference, but much more important, the web is already used to dynamically typed languages, for better or worse. You can argue about it, but that's where our demographic is. There's been many years of work on this idea because somehow people want to have the advantages of static typing, but they don't want the disadvantages. And I'm not really doing a really academic talk with a lot of space spent time on related work, but these are some of the highlights going, as usual, it's all been done first in Lisp. I'm not even going to contest that. The scheme people did a thing called soft typing, a particular approach that they did probably more academic work than anyone else in that area. Cecil, Erlang, there's an optional type system of some sort, or non-mandatory. Again, I'm going to try and define what optional typing means to us in a more narrow sense. Strongtalk was a Smalltalk dialect that worked on many years ago with Lars Bach, who's really the father of Dart, as it were. And one of the Strongtalk was significant, perhaps more for the engineering work done that was eventually became a precursor to a hotspot virtual machine in Java and so forth. But it had, lots of other innovations for the time, including an optional type system. And then there are a couple of others. There's a lot of recent work on gradual typing. Probably a lot that I've forgotten. There's a workshop called STOP where people discuss these things every year. So there's a lot of work on this. But the one that we're interested in, or I'm interested in, is of course the one that I worked on. How could it be different? And it's important to this talk because it is, in some sense, the direct precursor of the work we're doing on Dart. So the idea of optional types, as we see them, is, of course, they're syntactically optional. Everybody gets that. But the important thing is that they don't affect the runtime semantics. And this is actually a surprisingly difficult thing for people to grasp, because every language that has mandatory types, you find that somewhere or other the actual runtime behavior starts to depend on what those types were, which is very different from, say, lambda calculus, where the thing works just fine with or without. It works better without the types, but the types don't change anything. They tell you that something might be a problem, but they don't change the reduction rules or anything. So we're more in that spirit. So what does it all look like? Let's try and have a look at an actual program. So this is Dart running in the browser. In a way, it's actually a local copy of an application that you can go to on the web at try.dartlang.org, and you can basically type in a Dart program and it will evaluate it for you. So in this case, we have a class point. It should be fairly obvious to everyone what this sort of thing does, right? There's a class point, has instance variables x and y. It has a plus operator that lets you add points. It has a scale method that will scale the point by some factor. You can compute the distance from the origin, that sort of thing. And there's a main function, which you might guess is the entry point. And it produces a couple of points, adds them, and prints out their distance, the distance of the sum from the origin. Okay? Now, this is all a completely dynamically typed program. You'll notice that there aren't any types here. There are constructors that are creating types points. There is the constructor declaration here. There's a bit of sugar that basically what this means is that this constructor takes its two arguments and immediately assigns them to the corresponding fields, the two arguments. So you give it two arguments and it assigns them to x and y, and since people are too lazy to write all that, they thrive on sugar like this, and we're only too happy to accommodate them. So this is all fine, and we can run this program, and it tells us, you know, that the distance of this thing is 50 from the origin. That's nice, but we can, what's a little unusual is, right, we can start putting in types here. So we can say that the two coordinates are numbers, and nothing has really changed. And now we have a partially typed program. But it doesn't matter how many types we put in principle, nothing, it works the same, right? These things are annotations. Our purpose with types is largely documentation for the humans who read the programs, for the tools that inspect the program. So people love name completion, various features like that in the development environment, and it's a lot easier to provide those if we provide the machine with this information. And we're not hung up particularly if that information is right or wrong, which is the strange thing, right? So if, for example, I was to say that this was a string, this is nonsense, but we can do it. And okay, so this is a premature example. You don't know quite how evil this gets. No. There is an interesting approach. There's a question of how you read these things. But let's not get ahead of ourselves. Okay? So apparently, we're quite happy here. But let's do something that should make it unhappy. Eventually, if we put enough strings, we will make it unhappy. Right? So, okay, so this thing is telling us that a point can't be assigned to a string, which is no great surprise. It's creating a point, and we've declared it to return a string. But you notice that it'll keep running just happily and doing the same thing. The fact that these decorations don't affect the semantics means that it doesn't really matter what I write here. And this is on purpose. So the idea here is that we have a large body of programmers who haven't seen a type in their life and are in no hurry to meet one. And they should be able to ignore typing altogether. On the other hand, we should be able to give people some meaningful messages about errors. We should be able to use this information for name completion, for all these things. And so there is actually some positive value in these decorations nonetheless. In fact, from my experience, most of the actual value is in having that documentation as opposed to the common approach of saying, well, it's great for detecting errors. With good programming environments, those errors get detected very early. I don't actually believe the common assertion that there's a real difference in robustness between programs written in these languages. So that's one thing we can do, and we'll get back to the question of why it didn't complain here in a minute. But let's continue with our regularly scheduled program. So far you've seen it's a very, vanilla-looking language, except for this strange business of the types that don't, that give you messages but don't actually stop the program from running. Reasons for that I just went through, and this is an ordering that I believe in terms of their importance. Now, in reality, evolution-wise, this is the one that put types on the map. All the rest is just commentary. Nevertheless, we're now at a stage where we can get pretty decent performance out of completely dynamically typed code. And for the kind of applications we're seeing on the web, it's not particularly critical. Early error detection is what a lot of people like to talk about, but in fact, it's not particularly crucial. What is crucial is documentation for people and for machines. And it's also a useful way to think about modeling your program, right? It's good to have those types to give you a mental framework. So those are the things that actually are important to us. What's less talked about is the downside of types, right? This usually deteriorates to a religious war of one kind or another, but they're all Turing complete and all that. But there are things that you find are difficult to express in a particular type system. And if you build a type system that lets you express that, well, that's lovely, but it gets so complicated that only a few logicians are really comfortable dealing with it. Now, there are a lot of people who are quite happy to live in the world that a given type system provides them, and but we're not among those. And I can give plenty of concrete examples of things that are handy to do engineering-wise that are just very difficult to express. Another issue is that typed languages tend to impose a workflow. They tend to make you work in a certain order. They tell you things are missing, things are not declared, things are inconsistent, and please make them consistent before you proceed. On the other hand, we find that it's much more fun to work with something that is less constrained. Starting with the old read eval print loop, but going into environments where you run something, the debugger pops up, and then you fill up the missing method. Right? You actually build your program from the outside out, outside in. You can write a test. There's nothing there. It immediately crashes, but it doesn't force you to go back to the beginning. It lets you incrementally, interactively build your program. People who worked with these environments, things like list machines, Smalltalk, Self, get addicted to them. People who haven't worked with them don't seem to get it. But we don't want a language that imposes a workflow. There is, and this is a separate talk, which I've given in various forms, an issue with the brittleness of mandatory typing, of the overwhelming temptation to rely on it for everything, for security, for optimization, and the experience I've had in the Java platform where everything relies on that thin layer of typing and that thing collapses. It doesn't actually work. So that's a different talk, but the point is there is a downside to traditional typing. So optional types is kind of a have your cake and eat it too approach, at least to some degree. So we get the documentation. Now we admit that documentation might not be actually correct because we are no longer necessarily in a position to prove it. We still get the conceptual framework. We often do get the early error detection. Again, not guaranteed because we're not necessarily, fully typed and so forth. And sometimes we can even squeeze some performance out of this thing because sometimes it's easier to prove something given these annotations than to infer them and try and optimize. But that's really very much attenuated and not our focus. So there are a lot of things you can't do with optional typing. There are certain language constructs you just can't have. Type-based overloading in Java, for example, is what you actually call depends on the static types that you wrote. We can't do that because that would violate this core idea that the types don't affect semantics. The one thing that's been bothering people in Dart, I admit, is that, for example, we can't decide how things get initialized based on the type declaration. So we can't have a sugar saying, you just write an int and we'll initialize it to 0 for you, which people are kind of used to. Because it's a pure object-oriented language in the Smalltalk, Self tradition. Everything's an object. Dynamically, we know nothing. Basically, we initialize everything to null. And null's an object, too. There are other interesting things, C# extension methods. But by far the most interesting one on this list is typed classes, type classes as in Haskell. One of the few examples of a construct where I actually want to have if I had the types. Most of the others I'm very happy to dispense with. But it is sort of an austere discipline. So at this point, somebody might ask, okay, this is fine, but what's actually new? If anyone who follows this literature knows that, didn't you do this 18 years ago or so? And to a degree, we did. Not many people paid attention, so we can get away with doing it again. But that's not really our motivation. The point is, there's always this gap of decades between doing something as an initial project in research or a startup or something and hitting the mainstream. And we think we're ready for the mainstream. That's one point. This screenshot is that Smalltalk environment I mentioned, StrongTalk, and you can't probably read it from here, but this is the hash method on object. It's got a type error because it doesn't declare itself to return an integer. And the complete interactive system, of course, continues to work. And if you know anything about how these systems are built, you know that if it was really wrong, it collapses in a rubble of bits instantaneously if something like hash wasn't working. So again, the idea that the type annotations don't necessarily mean anything. And we sort of stumbled on this approach because it was a dynamically typed language to begin with, right? That keeps you honest. We didn't have the option initially of tampering with its semantics. But there are differences. There are a couple of differences. And one is that really Strongtalk, well, the idea of an optional type system, I found, at least in previous talks to sort of theoretically oriented audiences, to my surprise, did not perturb them at all. They're quite happy with that, as long as the type system is sound. And Strongtalk was, I believe, a sound system, though we never did the Greek to prove it, but we had basically taken the formalism and implemented based on Kim Bruce's work, which did all the Greek that you would want and more. And, you know, that was fine. But here we're not really building a type system in the conventional sense. You can build one, and I'm sure that, you know, in 6 months, 20 academics will, and we welcome that. But we haven't. This is really a type assertion system. And what's different is we support a mode where we can use these types to drive assertions in what we call checked mode, so that we can actually, as the program runs, find out dynamically if some of these annotations are being violated. And that, again, is a very pragmatic thing. It's something we didn't have before. But that's really the way to think about this, and I'll show this in a minute. And the other thing is, for various reasons, as you'll see, the type system is quite deliberately unsound. And this, of course, drives some people, you know, to almost homicidal levels of anger. But we're really, you just have to interpret it as something else. This isn't a conventional static type system. It's not intended to be that. So essentially, the check mode, as I said, lets you interpret type annotations as adding assertions. So if you write that there's a variable x of type t and you assign it an object O, we can essentially insert an assertion. That's the one right here. And check dynamically, is O the actual object, not the static type of that expression, but the actual object O that's being assigned at runtime, is it in fact a subtype of T? And this is a mode that we run. It's intended for development. Basically, the fact is it's just way too expensive to run it in production, because every place a value gets transferred. When you pass a parameter, when you assign, when you return from a method, we do these checks. And that's really handy for the developer, because it tends to localize error handling very, very quickly. But it is, unfortunately, too expensive. And you can certainly make the well, I wouldn't. It's true. There are programs that run in production just fine, even though this thing, you know, dies on them, right? But what it's really telling you is your type annotations are inconsistent with what's actually happening, and that's a good prediction, as you say, of that something is probably wrong. So let's go and do something about this. So if we were to hello, hang on, I need to move this a little bit. Yeah, okay. Last time I gave this talk, the screen had, I guess, bigger resolution. But this little thing turns on check mode. And then we'll run it and see if anything has changed. And so, yes, we have these beautiful red letters, which are hard to read, but do have the property that they indicate that some, you know, people intuitively associate red with a problem. So, in fact, we found that you know, the runtime type of which is, unfortunately, it's a young implementation, so this is a somewhat mangled name, but basically point is not a subtype of string. And so it's, you know, stopped the program in its tracks, even though we know for a fact that it runs. But it does tell us that there's something broken about our type annotation. So if we were to put something a bit more rational here, it'll probably die at the next point. Right, so we need to fix this. So let's say that this is a point 2. And now everyone's happy. Right? So this is, you know, I don't have time to do an exhaustive demonstration of this thing, but you get the idea. The development process interactively does benefit from having these type annotations, but at the same time, you are not constrained in any way by them. And that does attenuate to some degree what we can get from them, but we think it's a worthwhile compromise, depending on the tooling, on the environment, and so forth, and we intend to provide a lot of those things. Now, there's other aspects which may be even more shocking. So here we have this little program. And it's meant to illustrate a very common situation. People have heterogeneous data structures. Various things are stored in them. So there really isn't a very meaningful type you can give to anything that fetches data from that structure. So we have a trivial example of this. This is a literal map here. It has two entries, one under the string Frankenstein, one under the string Dart is great. And of course, under Dart is great, we say true. Well, how else? What else could it be? And under Frankenstein, we have a string called doctor. And then we have, we call this lookup function. We look up Frankenstein, we assign it to a variable, and we print this and do string concatenation. So it will, if we run it, we hope to see Dr. Frankenstein. Now, this is a partially typed program. And so we might decide that we really want to annotate it more. There are no doubt going to be many people who are much more comfortable fully annotating their Dart programs and making them look a lot more like, say, Java programs. It's not necessarily what we recommend, but people are free to do that. Now, if we do this, we find that there's a complaint because there's no plus method on object, and title is an object. Note that before, when we had no declaration, there were no complaints. The idea is that essentially we associate a type dynamic with anything that doesn't have a declared type, and the type dynamic behaves sort of magically. It supports all methods and all callers, and it basically is a subtype of everything and a supertype of everything. It's logical nonsense, but it has a nice property that it makes the type checker shut up, which is what people actually want. And so we're driving this more by ergonomics than by, say, mathematical logic. So what should we do here? Well, we could say this is a string, right? And now, if we run it, everyone's happy, except that somebody should be piping up, and I actually showed this by mistake or too early before, was that, right, you're now assigning an object a string, and shouldn't somebody be complaining? And so, as a practical matter, again, we're not building this as a traditional type system. This is a tool in the service of the programmer, and what works heuristically in practice most of the time in a dynamically typed language is what we're concerned with, rather than some abstract notion of mathematical correctness, which, by the way, is, you never get out of a type system anyway. You get a very partial notion of correctness, right? So one finds that in these situations, which are very common, that this kind of, this kind of casting goes on. And we could, of course, give a warning and require someone to write, a cast or something. But this puts you in a mode which is all too familiar to people who work with these languages, of battling the type checker. Right? There's nothing wrong with the program. It runs. I know for a fact that when I look up this key, it's going to be a string. It's an invariant of my program. But I am forced to spend my time doing battle with this beast. We don't want our users to do that. Many of them don't come from a culture where they're used to doing that. They will not gladly submit. And so we deliberately choose to not report all possible type errors. And this, throws a lot of people for a loop, but it's a very deliberate choice. It's one of several choices that generally make this if you view it as a traditional type system, it's unsound. Now, you could easily treat it as sound by interpreting these annotations differently, and I encourage whoever wants to do that should be able to, in pretty short order, create a tool that will behave like a traditional type checker. But it's not something we want as the default mode of working for this language. So, we talked about checked mode. I think I just said most of this, right? It should be viewed as one more tool in your toolbox, a static analysis tool based on a bunch of heuristics, and it's coupled to a dynamic type assertion mechanism, and it's just a useful thing. And again, if that doesn't convince you, and I believe that most of the people who believe in that sort of thing cannot be convinced by any means, humane or otherwise, then of course you can interpret the type annotations as you will, right? You can write a tool that will scream bloody murder about these things. What you can't do is prevent people from running their programs. Now, again, I really want to emphasize this point about not constraining the set of programs we can write here. A classical, and in doing so, not constraining the execution semantics by the type system. Classical situation we typically see is execution. Obviously, there's a type system in a language. It depends on what you wrote as executable code, whether you can type check it or not. It's obvious that the kind of types depend on the kind of entities that you have in your language. What's rather strange to me is how you all invariably find that the opposite is always true, is also true. That what your program does depends on what you wrote in these type annotations. I actually find this very perverse, but it comes from this knowledge is power and all power corrupts. And types give you knowledge about your program, and people cannot resist using them. So we really want to just have this thing go one way and make things more decoupled. And this has nice properties. As a language designer, it means we can evolve the type system happily, independently of our real executable language. Having evolved, having gone through the pain of trying to evolve a major language's type system in a significant way and never ever wanting to do that again, I can say that it's really not liberating to not be constrained this way. If someone comes up with a new clever type checking approach, we can add those tools, and it doesn't require us to rejigger everything because our execution engine doesn't care. Question comes up a lot, type inference. People are very lazy. They hate typing stuff, and so they would like the system to do this for them and figure out what the types are. And I'm happy for tools to do this. I'm not happy for the language to do it. Again, there's an analogous situation, right? Type checking to type inference is very similar to execution to type checking, right? One direction of constraint is necessary. What types you infer will depend on what kind of type system you have. But making the type system you have depend on what you can infer. And the classical example being Hindley-Milner means that your type system won't be good at certain things. You're going to have to restrict it in some ways, and we don't want to do that sort of thing. So again, we want to do something like this. And this, again, is wonderfully liberating. You can now write type inferencers in your IDE that work on, the phase of the moon, right? This actually can be useful. I mean, you don't actually have to have a sound type inferencer. You can guess things based on naming conventions. You can use all kinds of heuristics, and then you can put in these types. And if they're not true, the type system will tell you, but you have not, tied yourself into knots. And so this it's a question of how small a box do you want to live in? Right? There's a space of executable programs, there's a space of programs you can type check, and there's a space of programs you can type check with a system that you can reliably infer. And there are a lot of people, very smart people I know, who are quite happy in the little red box. They argue that the little red box gives them such advantages that it's worth it, and there aren't interesting programs that you can write outside the red box. And obviously they don't write the many interesting programs that are outside these two boxes, right? People on the web actually do, sometimes gratuitously, sometimes not. And so we're trying to be very, very forgiving. Now, a few words about more details of how this thing works. Interfaces, essentially interfaces are roughly what you'd expect from, say, Java. What's different is that the type system works exclusively with interfaces. So there are no types that tell you that something is a given implementation. Right? Every class implicitly produces an interface that describes its behavior, and that is what we use to type check. The interfaces are reified at runtime. You can test these things. The usual instance of thing, it's called is for some reason that I'm not sure of, but it essentially is like instance of. And this has interesting implications. For example, you can go and implement the interface of some other class completely independently of subclassing it. So you may not want its code, its representation. You just want to fake it. This is very common in all kinds of situations, testing being a simple example, right? People mock up examples of other types. And that's to me, this is really the core of what's actually good about object-oriented programming. Object-oriented programming is not necessarily all the baggage that the world knows from Java and C# and C++. The core idea is that you only depend on what the externally visible behavior of something is. And as long as you can fake that behavior, you can produce any kind of thing, whether it's a proxy or a mock-up for testing or things like that. So it's very, very important to us to maintain this. On the other hand, as you'll see, there are some interesting trade-offs to be made here. I can't really give a talk about types without my long and tortured history with generics. So let's look at generics. I've done generics several times. Maybe eventually we'll get it right. Who knows? So we've got basically a little program here that does a bunch of dynamic type tests on generics of various kinds and prints the results. So things like whether a list of string is a list of object and so on. So again, this is one of the places where we and the logicians have parted company. Because this is an unsound type system. List of string, for our purposes, is a list of object. Covariant generics. This is well known to be logically wrong. However, after some years of trying to get this idea across to a broad swath of programmers, I've decided that this is ergonomically incorrect. It just cannot be plausibly done. There are too many people who constantly misunderstand it. In fact, almost everyone misunderstands it intuitively, right? You can train people, you can show them what, Cardelli's papers, and everyone will understand this. But there's a very strong intuition that people seem to have about this. And rather than fight it and have people puzzling over type errors that they cannot really understand, we've decided that since we're not dependent on this type system in the same way as, say, a language like Java is, right? Nothing will happen if the types are wrong. It's dynamically a pointer-safe language. We can afford to simply have a rule that isn't correct. That means that in some cases we will not be able to give you, absolutely correct assurances about your program. But it also means that we are trying to avoid, we will never have to have a programmer scratching his head over what does contravariance mean. And the fact is that for the vast majority of people using this language, it means absolutely nothing and never will mean anything else. So having said that, we can run this and see what the thing says. So yes, a list of string is a list of object because strings are objects. What could possibly be wrong with that? Lists of objects are not lists of strings because not all objects are strings. This is something that people seem to be quite comfortable with. List of strings are not lists of ints. The last two are kind of interesting. So again, if we're saying that types are optional, that means that we can't always be passing these type arguments to things because there are lots of people who don't want to deal with this stuff. So you can write list and without passing a type parameter, as we have right here. What does it mean? It basically means list of dynamic, where dynamic is this magical type I mentioned that says we don't care about the type, right? And by covariance, in fact, since dynamic happens to be a supertype of everything, a list of string is a list of dynamic. That isn't necessarily very safe, but again, we want to confront people with errors only when we're very sure they're errors, and only with relatively ground concrete entities. We do not want to have people having to reason about higher order things. This also applies to the rules for function types, for example. So every list of string is a list. Well, again, explain this to a guy in the street. It's a list of string. Of course it's a list. If you can't explain it at that level, you have a problem. So the last one is perhaps the most puzzling because, well, you can certainly argue that not every list is a list of string. But here again, practicality has this nasty habit of intruding. We expect to have a lot of libraries with fully typed interfaces. We think that's a good thing. It gives people documentation. It tells them what they need to do. However, what shall the programmer who doesn't write types in their program do when they pass, for example, a list that doesn't have a particular type to an interface that says it's a list of string? They will probably find out that it requires strings, and they will produce a list that contains strings. But a list that contains strings is not type-wise necessarily a list of string, because these are mutable lists, and you could later shove something else. Explaining all this to people is a waste of time for everyone concerned. So we actually take the position that, yes, a list is a list of string. So that's generics in a nutshell. I've done it with variance annotations at the declaration side, I've done it with usage variants. I've done it in many ways. And we're trying something new, because those ways, we do know from experience, don't work very well. So, you might ask, well, you're reifying these types, right? We do actually, unlike in Java, we have the opportunity of starting from scratch and actually having these type parameters for the generics represented. We also have the interfaces. So they do seem to affect something that's being executed, right? When you actually ask if something behaves as a type, there's something there in the runtime that is influenced by the types. Now, in an object-oriented language, you always have the classes reified, right? Because that's necessary for the actual machinery to work. In this case, we also reify type arguments to constructors. And we also reify the interfaces. But as you can see, they're optional. And under the covers, what happens is we pass this magical dynamic type and store it, and it's represented at runtime. And type tests are a dynamic construct that is looking at that reified information. And that's how we square the circle. Carl?
Can you give a name to this magic dynamic type?
Yes, you can. And pretty soon the implementation will catch up with the spec, and I'll be able to demonstrate that. The annoying thing at the moment is that it doesn't actually work. It is called dynamic with a capital D. And yes, and sometimes that's convenient. If you have only one parameter, you can sort of omit it in the case of lists. But say you have a map that maps strings to whatever, and you really do not want to worry about what that thing is, it would be handy to say map of string to dynamic. So it's actually possible and useful, and will actually work fairly soon. Oh, another thing I sort of have to emphasize is how early in the game this is. Right? This is by no means a product. This is a very, very early stage of development, and we put it out there for people to comment and complain and experiment and so forth. So the summary for optional types, as it were, is there is a static checker that provides warnings. There are no type errors. And it is tuned to be unobtrusive. That is, it doesn't try to catch every possible error. And the types don't affect the semantics, except that you can, essentially during development, you can view this as a special kind of debugging mode, right, where you can turn all these assertions. Many systems have a facility for turning on asserts only during development, because the asserts might be too expensive to have all the time. Yeah?
So in terms of reasoning about program behavior in production environments, it seems like type annotations in this language almost kind of trick
They're not intended for that.
Right. So I guess I'm just curious, have you had any experience with what people feel about the debugging experience, given that the type annotations are not actually in any way?
Okay, so our experience comes from prior efforts, right? At this stage, we haven't quite, the debugging tools for Dart are still quite rudimentary. Having had many years of experience with environments like Smalltalk, including a optionally typed Smalltalk, we find that reasoning about your programs is not necessarily the critical thing that these annotations are for. I could live very happily without that. There is a religious controversy that I cannot resolve by peaceful means, at least, on this issue, but they're not intended for that. Yeah.
In terms of confusing the debugger, the person doing the debugging.
So if the person doing this debugging begins to believe that these types are somehow guaranteeing something, is what you're saying, right?
Thinks they could be in some sense reliable, where that's really
right. Well, basically, they believe, if it says an int, it should be an int, and yet it isn't, right? So this is something that, if you're coming from a dynamically typed language, you don't have these expectations. The question you're raising is, if by giving these annotations, which may in fact be complete lies, there's an issue for some people. We don't have a lot of experience. The experience we do have internally at Google is that people love this system. They really like working this way. Now, does this guarantee something about the real market out there? Unfortunately not. This is something I know from bitter experience. All the people, not all, but a vast majority of people who commented on Java generics like them. They by no means represented the people who actually use them in the end, because early adopters, the people who are willing to try something like this, are sort of the tail on one edge of the Gaussian of the community. And most people, they'll only use it when it's a product, by which time there's nothing you can do to fix it for them. But that is the sad reality.
Which side of the tail are they on?
I'll let you guess
Typically
that.
on the expert level, or I don't know.
The early adopters are very much on the expert level, right? The vast majority of people do not. They have jobs. They have a lot of things to contend with, and they are not naturally fascinated by the extreme edge of technology in that same way. They don't have the time. They don't want to expend the effort. They will do this because it's out there. It's the new thing. It's part of their job. They actually have lives outside of computing, and they don't do this. So,
bad coding.
Okay, I can address the criticism. I can address, it's a religious point, since of course there's nothing behind this to state what bad coding is. Programming without types is not bad coding.
But writing something that isn't strictly correct but still runs is, from my point of view anyway, bad coding.
There is a school of thought like that. There's a school that says that you should prove your programs correct.
I'm not saying that you should necessarily have types, but if you have types, then using them correctly would seem a wise move.
That's a widespread opinion among a lot of smart people. We disagree. That there's simply...
So it's okay to write bad code?
I don't think it's bad code. I think that getting in people's way when they're developing is a bad idea, because that encourages bad code.
Nobody would disagree with that.
Obviously. And so that's why we're doing this. We are not imposing a workflow on people. We are not imposing a static discipline that inherently will always mean that some things cannot be effectively expressed. It's just it's a question of a value judgment of what the value of these annotations are. Every practical language has holes in its type system, whether it's a cast or...
Software engineering is poor discipline, and let's embrace the horror.
If you want to put it that way, you're entitled to that. You won't get me to do anything except violently disagree, right? So this is kind of the kind of religious argument that gets people nowhere. We are building a system that lets people who are would otherwise be using something like JavaScript build programs gradually. If they feel the types are valuable to them, they can use them. They can use tools that, no doubt will show up that will interpret these annotations more strictly if they feel that's valuable. But they don't have to. We're not in a position to impose it on anyone, and we wouldn't, even if we could. Yeah?
Is it really that expensive to run everything in debug mode? We have all these optimizations for et cetera, et cetera. Couldn't we just run everything in debug mode?
Well, we certainly do that a lot of times, and maybe as things mature, we'll find it differently. But it's one of those things that's much more pervasive than you think. It's much more expensive right now, and as far as we can see, for quite a while to run debug mode. And check mode is what right.
Check mode.
At the moment, it is way more expensive. And it seems that it would always be significantly expensive. If it isn't significantly expensive, then things might change. But again, it's not our approach. There are programs that will run just fine, even though the check mode traps them. So there's two questions here: whether you should always do it, or it's really up to you. If you find that it's fast enough and you believe in that's a fine thing. Yeah.
Maybe you said this again, but can you please say again on what is the intended interpretation of the type annotations? So let's say I'm writing code in JavaScript where I have no types right now, and now this thing called Dart comes along. So what is my interest in moving to add type annotations if they don't guarantee correctness? So, what is the intended purpose?
The intended purpose is documentation. They give you an idea what it's about. And they give your tools an idea about what it's about. And yes, it's not a formally verified guarantee. As for guaranteeing correctness, types don't guarantee correctness. Types only guarantee us very small and not particularly significant set of issues that might not arise. So it's not about that. As I said, it's not at all about trying to guarantee correctness.
In documentation, right? Documentation I can just do with comments, but you also have this tool that does some checking.
Right.
So what?
It's a heuristic. It's something that does checks that seem to be of actual practical value to people.
Yeah, but
Not all these checks are equally valuable. It does these checks, and the checks will give you warnings, and in fact you may decide to ignore them because you know something the type checker doesn't, as opposed to a conventional system that will simply prevent you from building your program. Now, as sort of I expect in a forum like this to get that kind of feedback, it's interesting we get a lot of feedback from the other side, which says, well, is it dynamic enough? Can I do all the strange and wonderfully warped things that I like to do in a dynamically typed programming language? So, for example, no such method. No such method is, it goes by different names. In Smalltalk, where it originates, it's does not understand, right? Is this catch-all that lets you basically define a trap that when a method that is not defined is called, you will then, rather than necessarily throwing an exception, which is the default, you have the opportunity to define code that will respond to that. And it'll get information about what was called, with what arguments, what name, and you can do all kinds of wacky things. You can add that method on the fly. You can, for example, write forwarders or proxies or things like that that will take care of all the traffic that comes to them without knowing in advance what it is and without defining all those interfaces. Things that are bloody awkward to express with a type system. So we do support that particular feature because we think it's enormously useful. There's also this whole business of being able to do reflection, to modify code, and so forth. And again, we have not yet added it, but the debugging API and a mirror API that will allow people to do that sort of things is going to materialize in probably a couple of months at the most. So we definitely are a dynamic language in that sense, in the sense of actually the code perhaps evolving dynamically. We'd like to stratify that. We don't like the way that JavaScript, Python, and company do that, in the sense that there is no layering, right? Variables come into existence by virtue of typos, that sort of thing, right? We prefer a layered approach where there is an API to do reflection, can do introspection. It can perhaps do other things like add methods dynamically or change the structure of the class or things like that. These things let you do very interesting tricks. They cannot really reasonably be handled by static type disciplines, and we value them. So yes, it is a dynamic language. And one of the problems with questions, of course, is that we do tend to derail our time schedule, but yeah, okay, I'll torture you some more then. This is sort of the main point. So abstract data types without types. At least you'll get a bit more information about Dart this way. Dart has this notion of libraries. It's a very, I'd say, simple-minded notion. Libraries are collections of top-level definitions, classes, interfaces, and functions. They can import each other. They can refer to each other in a mutually recursive fashion. And they act as units of encapsulation. So essentially, privacy in Dart is something that follows, I guess, again, the conventions that these communities are quite comfortable with, even though you might question them, right? So it's based on names. So naming and privacy are not orthogonal, and I can understand the objections to that. Basically, if you preface a name with an underscore, it's private to the library in which it appears. It actually does have some advantages. It's context-free. Anyone looking at this code can tell whether something's private without, going to the definition and so forth. It makes our life as implementers easier because we know that as well. On the other hand, yeah, it's not so pretty that I'm constrained in the naming and so forth. But what's really interesting is how this relates to the interface-based type system, right? So abstract data types in the classical sense rely on the fact that the type system recognizes a particular type. And there are multiple instances of this particular type, and there's a layer where it gives you access to the internals of that type, and there's places where it doesn't, but it knows that it's a particular type, a particular implementation. when you're doing interfaces, of course, the whole idea is that anyone can mock that up. And can you reconcile that? Basically, these things seem to be very much in conflict. And so if I haven't horrified you enough, I'll show you how we can actually do that. So to make this a little more concrete, suppose I have here a class A with a private variable, underbar foo. And I have some top-level function that takes an A and returns this. This is a shorthand notation. Basically, you can read this as return A dot underbar foo as the body of this function. Okay, so this is very much an abstract model of the typical classic ADT with a stack and a pop and push method, and the stack inside has hidden, whatever array or structure that it has. And these methods access values of type stack by getting at their internals. Now, when you actually start to think in terms of interfaces, and you find that writing something like this, a different class that implements A, well, it doesn't have, it's implementing it. It's not it's not inheriting, it's not subclassing it. It's not extends. It's implements. I assume everybody's sort of comfortable with Java, and so it doesn't actually have an underbar foo field, and yet I should be able to pass it, right? Since it implements A, I should be able to pass a new B into this foo function, which will want to get at underbar foo. And what's more, if I declare this is a getter here that implements underbar foo, this is private to a different library because it's in library 2. So what would actually happen at runtime is that I would get a dynamic error because this B doesn't actually have the underbar foo that the first library is looking for. So, and yet we want to be able to mock these things up and support them for all these purposes, like testing and proxies and so forth. So there's different things we might do. We could issue a warning here telling you you're not really implementing what you want, but this has rather nasty properties in terms of encapsulation, right? Because, okay, we give this warning. First of all, that means that as code evolves and people add private stuff to their classes, suddenly code that used to work breaks, which is not a good thing. And what's more, what are you going to do about it? Okay, so you can't implement that underbar foo, right? So that doesn't seem to be very helpful. We could warn you here. For example, we could say, well, we're interpreting this as the interface A, and in fact, the interface A doesn't have a private members. It's only public members, and therefore you can't do this, which means that you can't write effectively ADTs. Personally, maybe that's what I do, but when you find that you have a large audience of programmers who are accustomed to certain idioms and styles, you have to accommodate them. Telling them what they should and shouldn't do does guarantee that your language has 5 users. So, what can we actually do? We can do things like this. We can define underbar foo, and we can define a trap for no such method, where we can actually check if, in fact, we were called with this private thing. Well, then we'll call our underbar foo and return the result. So we can use the dynamism of the language to work around the problem in the type system. Now, this is extremely pragmatic, and you can say what you like about it, but in a way it's really cool because it does mean that you can write both efficient binary methods that look in, that have access to multiple types. You can write classical ADTs where you want to. You're not constrained by the object level encapsulation that would be the natural choice here. And at the same time, you can take advantage of the interface-based typing and easily, for any given implementation, mock up something that can act as a proxy for it or as a used for tests and all the kind of things that people find incredibly valuable in practice. So that's kind of neat, and we can do that, again, this is another form of unsoundness, if you will. We can do that because we're not dependent on a conventional type system. We don't really, that's the advantage of a dynamically typed language. And if you don't like it, you can implement a checker that goes and interprets our annotations as non-invariant, or maybe you'd infer the variance by looking at the declarations. You can give all the warnings you want about all the things you want. And I'm not sure how many programs in practice you'll be able to type check that way, but you'll be pretty close to what you can do in Java, probably. So we don't see a downside to that.
If you have no such method,
Yeah.
Are methods of classes first-class functions?
Methods of classes can
Can
be
you extract
extracted.
it and call it with whatever arguments you want?
You can extract it, you can call it with arguments, but the receiver stays stuck to it, right? Because you don't want it to work on some other target. Yeah, built-in factories, this is kind of nice. Constructors have well-known problems. Essentially, constructors are a failure of abstraction. You can't, with a classical constructor, you are telling publicly that I want a new thing allocated. And the problem is you don't always want a new thing allocated. Maybe you want to look it up in a cache. Maybe you want to allocate something but from a different type depending on circumstances. And so there are, design patterns that work around this, factories and so forth. The problem with that is people have to read the books and be more knowledgeable to use them, and you find that a lot of people who should know better will have planted things that later don't work out very well as code evolves. And again, people who really, really should know better have done that. So the idea of factories is that we support factory constructors, which I call constructors without tiers, right? Which let you define things that look like constructors. So they're familiar to programmers. They can write their regular constructors and learn about this later, as it were. But these factories allow them to actually, rather than allocate automatically something, there are constructors that let them look things up in caches or compute things, etc., etc. So that is very handy. It, to a considerable degree, reduces the need for things like dependency injection frameworks. Not perhaps entirely, but probably by far the most common problem that drives people to use complicated structures like dependency injection is the fact that they tend to find that their code is hardwired to producing instances of a given implementation, a given class, and that later they would like to have something else. And so by this decoupling basically solves that problem. We can probably demo this. Factory. Right, so this is an example of this. So we have an interface person, and what's unusual is this construct factory here, which says that there's a factory, person factory, and that will basically serve to by default produce instances of things that support the person interface. So down somewhere in the bottom, we have a function that produces two new persons, and person is an interface, but we can still use it in such a call. And that means we're going to get some instance of something that supports the person interface. So if I want to produce some other kind of person, I can localize that decision here at the interface definition. What is the default mechanism for producing instances of this interface without having to go to all the callers in the code? So again, a very pragmatic and useful thing. You can also define what will actually happen when you call the person constructor here on this interface. It will call the matching constructor in person factory, which is defined as a factory constructor. So it doesn't produce instances of person factory. It produces instances of whatever it wants. It's just a method that computes, an object to return. And if you type check it, it'll ensure that the stuff is actually a person if you annotate it properly. So these are very small innovations from a sort of academic viewpoint, but they do have the property that they're really, really useful for people, and they're new and different. So is Dart done? Not by any means. Essentially every known programming construct has been proposed on the mailing list, and most of them we actually had already looked at and we've decided we might do them later. We'll see how things go. We can't do it all at once. Mix-ins, traits, etc. Reflection, obviously, we will do. We have a very, very low-level framework for very basic actor kind of stuff. Basically, just communicating through a protocol of arrays of values, if you will, and higher-level things that you can do on top of that: promise pipelining, Erlang-style pattern matching, C# awaits, or something else. These are things we're experimenting on and haven't really made up our minds, but something higher level needs to be there. So all kinds of ideas about whether classes can nest, whether libraries should be first-class objects, all kinds of cool stuff, whether we should support non-nullable types in the same optional discipline. because in fact that's one of the most valuable areas to get feedback on. Just to add to the controversy, I'd say that if I had to choose between a type system that just told me null versus non-null or a conventional type system, I'd go with the one that says non, because that's where the real runtime errors, manifest themselves. Metadata, more support for pluggable types, right? If someone wants to have a fancier type discipline, because we don't have a privileged one, you can add that and build a tool that looks at things. But right now, there's no nice way to make it syntactically palatable. You'd have to put it in comments or something if you needed extra information beyond R-type annotations, like variance annotations, for example. So there's all kinds of things we can do. We may or may not do. We're basically trying to get feedback from the community that's interested in this sort of thing and make our way from there. And that's really all I had. Yeah?
Are classes first class values kind of a beta E question?
At the moment, they're not accessible to you. They're reified, but you can't get at them, essentially. It would be easy to do that. There's nothing you can do right now with a class. They're not, because we're using mirror-based reflection, they're not a gateway to the reflective system, for example. There are no class methods. Again, there's a very conservative idea of static methods with pros and cons. We could evolve that and expose the classes as first-class values, but we're trying not to surprise people. Both Lars and I and others on the team have, if anything, found that the problem is not how to innovate, it's how to avoid over-innovating. If you want adoption, you can't get too far ahead of where the wider programming public is. Yeah?
I also recall you saying in your Newspeak lecture that pulling methods off of instances such that the instances are bound to the objects that they were originally defined on was not a good thing in terms of like mirror-based reflection. How has that changed?
If you want to find contradictions between this and Newspeak, I can feed you more information. Obviously, Newspeak is a very pure approach, and not everything done in Dart is something that I would say is ideal. What I think I meant, you can actually peeling the method off while the object is still tied to it is okay, right? You can just write a closure that does that. It's just a sugar for that. Peeling the method off independently of the receiver and then feeding in another receiver, that's a wacky thing that people let you do, and that's what I think I was commenting on. So on that one, there isn't a contradiction. But there's plenty of stuff that you can embarrass me by bringing up, like how Newspeak works versus how this works. That's fine.
Didn't mean to embarrass.
No, as you can see, it just falls off. But that's okay. This is a very different. The two constraints I laid out up front are what's driving this. They're very, very difficult constraints, really, and they're very different from an idealized project like Newspeak, where basically I got to do what I wanted. Yeah?
Will code that executes in the Dart VM have different performance characteristics if optimal types are provided?
Probably not. Again, it may, eventually, no one will ever complain if you get better performance, but that's not really the prime mechanism for getting performance. People who tend to tie their performance to types have had very disappointing results generally with dynamically typed languages. Now, in some cases, it might be the case that it would be easier for you to prove something. In fact, back in the Strongtalk days, we actually did this where we found that interpreting annotations for, say, numeric stuff as binding, it was easier to prove that something really was a number in that context, and then you could optimize on that. But it's not very high on the list. Okay. Yeah?
So my background is writing code that's going to run, server code that runs forever.
Right.
And I'm generally more worried about the obscure cases that I didn't think of, and having the compiler say, you didn't do something that makes sense to me over here. I consider it a real good idea to go look at that code.
So I'm not saying it's not a good idea. I'm saying that it isn't something that you want to tie in as a mandatory part of the programming language. You can write all the tools you want, and people will, that can go and do all kinds of analyses. One of the problems with a mandatory type system is that you find that after you've done that, people have a very hard time of extending that type system or adding anything else that they want, whether they want to check for race conditions or, there's a type system for everything. And most of them, people in the Java world, people have proposed a type system for everything, and most of them never go anywhere because it's just too damn hard and complicated to integrate that into the language. A language that has a nice reflective infrastructure and that doesn't, dictate that would allow people to actually do what I've called pluggable types, right? Where you can add as many of these analyses as you want and run them. And they don't interfere with each other because none of them have an effect on the runtime semantics, so they're not banging on the same common thing. It's fine to do these analyses if you find value in them. Point is, putting an analysis that prevents people from doing stuff because that analysis doesn't like it is not something that we believe in. You can write nonsense and it's fine, yes. You can also write very useful stuff that your static checker isn't smart enough to understand, and that is what we're concerned with.
Very large programs which may involve multiple developers or anything like that?
They can certainly involve multiple developers. That's been done with dynamic languages. There is a meme propagated by a lot of people who honestly believe it, that types somehow have something to do with the robustness of your code. I think that languages that evolve with a mandatory type system have the property that if you leave the types out, bad things happen.
Criticism of typing systems, which I'm not in total disagreement with, doesn't justify what you're proposing. I mean, it's true. Typing systems have a checkered history, and more work needs to be done. But to propose what you're proposing seems to me to be completely unnecessary and unhelpful.
Well, we find it extremely helpful, but we're just people developing, applications at Google. But I'd like to understand what bothers you so much about this, right? The alternative to this is programming in a dynamically typed language, right?
Well, I don't know enough about your typing system.
It isn't a type system, it's part of what I'm
your absence or your pseudo-type, whatever it is. I don't understand enough about it to be able to make a comment about it. It seems to me that what you're proposing, this ability to write nonsense and it be fine, is not okay.
So this is sort of makes it difficult to have much more discussion,
system, right? Polymorphism and so on have been around for a really long time, and there are different approaches to building typing systems, some of which are better than others. I think your general attack upon typing is unwarranted.
We're not attacking typing. We're simply not prepared to marry ourselves to a mandatory type system.
Yep.
Carl.
Yeah, I think that not tying yourself to the strong typing handcuffs, as in Java and C# is a very wise move, because that is just you can't write eval, for example, right? Where eval evaluates to anything, right? And give it a strong type, that's just plain impossible. And so therefore, you don't want the handcuffs. The only thing where I think it's somewhat questionable is not running everything in checked mode, because once you actually have said that this is of this type, okay, somebody wrote it down in the code, somebody might be tempted to rely on it.
So again, pragmatics. You can debate. There's two issues here. Even if you accept that position, there's a cost to that, and it's not a cost that seems actually plausible to pay.
Why do you think it's so expensive to do the checking?
Because,
for example,
well, there are umpteen programs written in this stuff, and they all run, depending 5 to 10.
You don't have to do all the checking at runtime.
Then you bind yourself into the approach that you're asking me to take, which is say I have a mandatory static type. That's the choice, right? I have to do these checks. If I want to do these checks, I have to do them at runtime because I cannot guarantee soundness given the other constraints that I've decided. It isn't a sound type system. You could take this approach of optional typing, which is what we did with Strongtalk, and say, you know what, these annotations you can write wrong, you can still write nonsense, but if I can check your program, that would be fine.
Quite significantly.
But
it's not about
you end up with a
burden of-
brittle. You always end up with a brittle program, where there's some change you want to make, which require you make changes through a bunch of other things that don't really have anything to do with.
Yeah,
the
I
problem
don't
you're trying to
really
solve.
want to skirt off into a typing discussion, because you're right, there are religious wars
Yeah.
there. My objection here is to the proposal that it's okay to encourage novice programmers to write nonsense and get away with it.
So people will write nonsense in statically typed languages as well, right? It's their program doesn't necessarily do what it's supposed to do. So I just don't believe that.
You've just described a number of lies that the programmer can tell and get away with.
They can write, in most languages, they can write lies. They put in a cast, and it turns out that it isn't true, and it turns out to be very late. You can write pattern matching in ML and still have it fail at runtime, right? Every type system has a backup mechanism. It's a question of degree. We're not necessarily encouraging people to write nonsense, right? We are trying to build a system that gets out of their way. And we don't see a way of doing the traditional thing and maintaining that level of fluidness and interaction. Yeah. And so, in fact, I'd argue on the contrary. We are potentially introducing a large community that wouldn't know a type from a hole in its head to the potential, to the value that you get from this, because it will find some problems for them, and they might actually be encouraged to use it more. How that plays out in reality is a big sort of social experiment that essentially we're going to be doing. But we obviously come at this from different axioms, and there's no way around that.
You mentioned a whole lot of interest inside Google. Well, what other dynamic language do they have a choice of using? They've got JavaScript, they've got
Python. So, unfortunately, they don't have the good sense to use Smalltalk, or Lisp for that matter.
the way the places that they can go is rather limited. So of course, if there's only 3 bars in town, you're going to go to the new bar.
That's fine with me. The point is that this mix works well for people. It does give them useful feedback while still maintaining that feeling of free interaction that many people really value, that you do not get out of a fully statically typed system. And so yes, this is new and different. It's not actually that new. We did some variant of this 20 years ago, and it's just it doesn't fit neatly in the traditional boxes. And I think that judging it by those criteria is the wrong way to judge it. Yeah.
Most of the objections you have to actually checking your type annotations at runtime really only apply if you allow the code to have a considerable amount of self-modification capability. And that was an issue about 2 years ago. The Facebook guys who were doing their internal PHP compiler or something made the point that one of the advantages there was that you couldn't dynamically modify the program, and that made compilation possible. In contrast, Google had the unladen swallow effort where you tried to do type inference and optimization on Python, and that failed horribly because Python allows so much internal modification. Even one thread can be changing an object underneath another thread, that if you accept all those dynamic modifications, none of the optimizations work.
So, to be clear, we're not necessarily advocating as many dynamic modifications as you see in those languages. Languages like Python and Ruby, you find that very often a lot of that is program setup, and a lot of it is somewhat gratuitous if you could do it another way, and it does mess with optimizations a great deal, and we're not necessarily encouraging that. One of the reasons that reflection is going to be stratified with a mirror system is it gives us much better control who can do reflection to whom and when, and therefore would allow us to optimize things. We're not encouraging things to quite be as randomly changing under your feet as they could be. On the other hand, both for sort of essentially social reasons, that the demographic we're after will not, they won't use ML even if we, tie them up and force it down their throat, but also for the fact that there are these cases where it just is limiting, and we do not want to tie ourselves to that discipline. And we do not, by virtue of, I guess, religious persuasion, believe that it is such a horrible thing. On the contrary, we find it very pleasant to work with. You can evolve your program. That's part of the gradual typing work. Is also the idea that you can move gradually from a very dynamic program. As things solidify, you can start, adding types and getting to something more concrete. In the interim, absolutely, things can be inconsistent. Learning to live with inconsistency is key here, right? Yes, you can write nonsense. That gives you the elbow room to evolve. It's not the end of the world. Inconsistency is a fact of life. You either, reject it or embrace it, depending on your persuasion, but we are not bothered by it. Because people don't ever, in production, write programs that they actually know everything about them and everything that will happen, and they certainly don't create programs that way. They are always in a state of flux. They are always trying to puzzle it out. See?
Yeah, logical inconsistency. They're easily reducible. You just write the spec. Windows does not crash. Fact of life. Run the program. Logical inconsistency. This is P and not P land. Logicians know about that. So, and the other thing is these large, everybody knows now, except for those hiding under rocks, that these large programs are full of inconsistencies of that kind. The documentation does not match the code. You've got 10,000 P's and not P's. Talk to the program manager of any large product.
I have a good idea that it's good that you two are sitting at a distance, because I don't have to do anything here anymore, because Carl's doing my dirty work for me, as it were.
That's unfortunate.
Yeah, but it's again, we won't get anywhere by having a religious argument. Yeah.
Is there any reason why isolates weren't mentioned? Because I thought that was an empty feature.
There is a reason they weren't mentioned. I ran out of time. Well, they were essentially isolate. They were mentioned, right? That's it's essentially a very simple actor framework. And if you're not exhausted yet, I probably am. So thank you very much for coming and enduring this.